Hi everyone, this is my second video in the series of solid state chemistry classes. In this video, we shall learn about Weiss and Miller indices. Before going to the core concept of Weiss and Miller indices, let me give some basic stuff regarding the solid states. We know that a three-dimensional arrangement of constituent particles will give a complete crystal lattice, or in simple way we can call it as lattice. And when you break the lattice, you're going to get a very simple repetitive unit which can repeatedly joins in all the three dimensions to give a complete crystal, and we call that as unit cell, right? And if you come with a cubic crystal, the unit cell will be written in a very simple structure like this. This is the simplest way of writing the unit cell of a cube, right? And here we'll be having corners, edges, faces, so on, and at each and every position we will be having one constituent particle from which actually the crystal is made up of, and we call that constituent particle as lattice points. And the lattice points may be present at the corners, may be present at the edges, may be present at the center of the faces, or the constituent particle or the lattice point may be present in the center of the unit cell also. And here we said this unit cell will grows in all the three dimension, so that to give a complete crystal, right? And this is x, y and z axis. And we know that the length of the edge along x axis will be a, along y it will be b, and along z it is c, and we call these values as edge length. A, B, C or the edge lengths, right? And if you consider a plane in a particular unit cell or a crystal, if you consider a particular plane in the crystal, in order to describe the exact orientation of the plane which is present in a lattice, or else we can simply say it as lattice plane. In order to learn about the orientation of the lattice plane in a crystal, we use two terms. They are called Weiss and Miller indices. So what we can say, this Miller and Weiss indices are used to describe the orientation of lattice planes. So in order to describe the orientation of lattice planes, we use the terminologies called as Weiss and Miller indices. And now we shall learn how to describe or how to say the Weiss and Miller indices. So first we shall go with Weiss indices. The Weiss indices or Weiss index is simply, it is the ratio of the intercept making by the plane in the crystal to the unit length of the axis. Unit length on the axis. That is the simple way of defining the term Weiss indices. That is, it is the ratio of intercept making by the plane to the unit length on the axis. I shall consider one simple plane, and from that we shall say how to give the indices, that is Weiss indices. And this is the origin, and let me consider this is the length A, this is once again length A, and this is length A. Or else let me change this one, B, 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 because this will be along y axis. Along x, let me consider this as A, and A. There are the unit lengths. This is C, C, and once again C. Okay, so here uh, this is one length B, this will be 2B, this will be 3B, and similarly from the origin it is length A, this is 2A, and this is 3A. Similarly it is C, 2C and 3C. If you consider one plane which is present like this is the plane we consider, and here this plane is present on the y plane and it is not oriented along z or x axis, it is oriented along only y axis. And what is the length it is covered and what is the intercept it is making from the origin? With the length of b. So if you want to give this indices for this particular plane, so this indices supposed to be said in this way. See, we have to take the intercepts making by the plane along each Cartesian coordinate, that is x, y and z, and there is no orientation of this particular plane along x axis, so that it will be taken as infinity. When the plane is not oriented along any one particular axis, we cannot say at what position it is exactly oriented, so it's supposed to be taken as infinity. And since the plane is present or oriented along the y axis at a length of b, so that intercept will be taken as b, and there is no orientation of this plane along z axis, therefore once again it is taken as infinity. And here we said in order to get the Weiss indices, we have to divide the intercept or intercept making by that plane by the unit length on the axis, right? So here these are the intercepts making by this plane along x, y and z axis. So infinity, the unit length along x axis is a, unit length along y axis is b, unit length along z axis is c. So infinity by a, sorry, infinity by a, you will be getting once again infinity. B by b, you will be getting 1. Infinity by c, you will be getting once again infinity. And these are the Weiss indices of this particular plane. Okay. So we have to take only the coefficients. Fine. So here we have infinity, 1 and infinity. This is the Weiss indices of this particular plane. And now we shall consider one more plane. We shall consider one more plane, and for that we shall try to say the Weiss indices. So once again, along x, y and z axis. Okay, and once again, sorry, b and b, and unit length a, one more a and one more a, and here it is c, c, c. And let me consider a plane this is the plane I have considered, and for this plane let us write the Weiss indices. Let us develop the Weiss indices. Yeah, let us develop the Weiss indices, and here we need to take the intercepts along the three axes, that is x, y and z. So here the intercept along x axis is, there is no orientation of this plane along x axis, so it is taken as infinity. Okay, and the intercept making along making along y axis 1, 2, there are 2b units, and intersect making along z axis is from origin c, and this is 2c, right? So, and we know that the definition for Weiss indices is intercept making by that plane to the unit length on the axis. So here infinity divided by A, 2B divided by unit length is B, 2C divided by unit length is C. BB will get cancelled, CC will get cancelled, and not an issue, we can vomit the A over here, and the thing is infinity, and here it is 2, and here is once again 2. And these are the Weiss indices of this particular plane. So in this way, we can easily develop the Weiss indices, and that actually gives, the Weiss indices actually gives the orientation of the plane along the each Cartesian coordinate in terms of the magnitude of the length or magnitude of the intercept making by that particular plane along each coordinate. Now we shall see the planes in a cubic crystal, and for that we shall try to derive the Weiss indices. Let us consider one cubic unit cell. This is the unit cell, and we shall consider the axis X, Y and Z. So let me consider X, Y and Z. Suppose if a plane is given in this way, let us consider fine in this way. Let me consider this plane. Okay, this is the plane I have considered, and here you can see this is the origin point, right? This is the origin, and you can observe this plane is having orientation along x-axis, and this point is having this plane is having orientation along x-axis and orientation along y-axis, but there is no orientation along z-axis, right? And we know that from the point of origin O till this point, the edge length is we'll get the edge length, and from this point to this we will be getting edge length, and we know that this is A, this is B and this is C. So we have orientation along x-axis, orientation along y-axis, and there is no orientation of this plane along z-axis. So now we shall develop the Weiss indices for this particular plane. So we shall take the Cartesian coordinates x, y and z, and here along x, so from the origin up to this point we have the orientation, so we shall consider it as A, and from the point of origin till this point we have the orientation, so we shall consider this as B, and there is no orientation of this particular plane along z-axis, so we shall consider this as infinity. So these are the intercepts of this particular plane from the origin. And now in order to get the Weiss indices, we need to divide these intercepts by the unit length. So unit length along x-axis is A, unit length along y-axis is B, and unit length along z-axis is C. So both will get cancelled, so you'll be getting 1, 1, and here by omitting C we can take infinity. So these are the Weiss indices of this particular plane. Like this, we can develop the Weiss indices for any plane which is given, so that it is possible to understand the exact orientation of the plane in a crystal. We shall consider one more plane in a cubic crystal. Let me consider one more plane, this one. So we shall consider the axis, and this is x, y and z axis. Okay, and let me consider the plane, this one. Okay, this is the plane and this is the origin. Fine. So this is the plane we have considered, and for this plane we have to write the Weiss indices. So Weiss indices shall write for this particular plane. So we need to take the intercepts making by this plane along each coordinate, that is x, y and z. And here along x, from the point, so this is the point, so this is the orientation. So this plane is having orientation along x-axis, and there is no orientation along y, and there is no orientation along z-axis. And this has a complete orientation along x-axis. So full edge is covered, so I can consider this as A. And there is no orientation along y-axis, so it is infinity. And there is no orientation along z-axis, so it is infinity. So and divide its unit length, A, B and C. These two will get cancelled. We will be getting 1. So by omitting these two terms, we can take infinity. And these are the Weiss indices for this particular plane. In this way, any plane can be given. For that, we can easily determine the value of Weiss indices. This is one way. And now, she'll go with the next thing, the most important one. Compared to the Weiss indices, Miller indices is more prominent in determining, in describing the exact orientation of the plane. And now we shall see how to obtain the Miller indices. In actual sense, the Miller indices are the reciprocal of Miller indices are the reciprocal of Weiss indices. So once you calculate the Weiss indices, from Weiss indices, it is very much easier to calculate or very much easier to get the Miller indices. And now we shall see how to get Miller indices by knowing the values of Weiss indices. Let me consider one set of Weiss indices. Let me take 2A, 3B and 2C. This is the Weiss indices I have, and for this I need to calculate the Miller indices. Okay, and this is the Weiss indices I have for a plane. So for this we need to calculate the Miller indices. It's a very simplest process. What to do in very first step in order to convert the Weiss indices into Miller indices, the first and foremost thing what we are supposed to do, we have to take the reciprocals for the coefficients of the intercepts. So here A, B, C are the intercepts and the coefficients are 2, 3 and 2. 2 along x-axis, 3 along y-axis and 2 along z-axis. For these coefficients we have to take the reciprocal. So that is, the reciprocals are 1 by 2, 1 by 3 and for this 1 by 2. So take the LCM for this one, and LCM for this thing is 6, right? So multiply each term with the LCM. So 1 by 2, 1 by 3, 1 by 2, you just multiply with 6. That is the LCM of this one. So you'll be getting 6 divided by 2, you'll be getting 3. 6 divided by 3, you'll be getting 2. 6 divided by 2, you'll be getting 3. And this is the Miller indices. Very much easier. Once you know the value of, once you know the value of Weiss indices, it is very much easier in determining the Miller indices. So let us consider one more example for determining the Miller indices with the help of Weiss indices. The Weiss indices value, let me consider the Weiss indices value, say 6A, 3B and 2C. This is the Weiss indices. And for this Weiss indices, from this Weiss indices, we have to get the Miller indices. So what we are supposed to do? First we need to take the reciprocals of the coefficients, that is 1 by 6, 1 by 3 and 1 by 2. And we need to take the LCM. For LCM for this one is 3 ones are 3 twos are 2 ones are 2 ones are. Again 6 is the LCM, hope I so. Yeah, 6 is the LCM for this. So 1 by 6, 1 by 3, 1 by 2. Multiplying with the LCM, that is 6. So 6 by 6 you'll be getting 1. 6 by 3 you'll be getting 2. 6 by 2 you'll be getting 3. So 1, 2, 3 is the Miller indices. And this way it is very much easier to convert or get the Miller indices by knowing the value of Weiss indices. Till now, we observed the Weiss indices with only positive sign, but we can have the intercepts with the negative sign also. If you get the negative sign, how to get the Miller indices? If the Weiss indices are having the negative sign, then how to get the Miller indices for that particular Weiss indices with the negative intercepts, that we shall see. Let us consider the Weiss indices 2a minus 3b minus 3c. This is the Weiss indices with negative sign. And what we are supposed to do, again, nothing, we have to take the reciprocals. So reciprocals are 1 by 2, minus 1 by 3, and again minus 1 by 3. And again, same procedure, we have to take the LCM for this one. So LCM is again 6. So multiply each term with the LCM value. 1 by 2 minus 1 by 3 minus 1 by 3, multiplying with the LCM, that is 6. So here I will be getting 3, and here I will be getting minus 2, and here also will be getting minus 2. But what the negative signs you get, that should be mentioned as bar. So this way we can find the Miller indices. So not supposed to say the negative sign while mentioning the indices. Just if the negative sign is there, means we have to write the bar over the value of indices, and there should not be any commas between the indices. It should be like this, and the indices should be mentioned within the parenthesis. So in this way we can convert any Weiss indices into Miller indices. This kind of questions are too regular in competitive exams like GATE, CSIR, or NET, or in JAM examination. Hope you understood how to calculate the Miller indices with the help of Weiss indices. This is one part. But the second part is, so till now, by knowing the plane, we determine the indices. Suppose if the indices is given, how to draw the planes? This is more curious one. So until now we saw that by knowing the plane, we can easily determine the Weiss indices, and by knowing the value of Weiss indices, it is easier to write the Miller indices. But by knowing the value of Miller indices, how to draw the planes, that is the most important one that we shall see now. So draw the plane, drawing the planes from Miller indices. Drawing the planes from Miller indices. And now we shall see how to draw the planes by taking the Miller indices. So let me consider one simple plane, that is 1, 0, 0. This is the plane. So now we shall draw, this is the Miller indices given, and now we shall draw the plane for this particular Miller indices. So this is the axis. Fine. X, Y, and Z. And here you can observe these things, this is along x-axis, this is along y-axis, and this is along z-axis. This accounts for A, B, and C. And here you can see this complete, it is having orientation only along x-axis, and there is no orientation along y and z-axis. That's why it is showing 0. That means this one. This is the origin, right? So the plane which is given in terms of Miller indices having orientation only along x-axis, and it is parallel to the origin. That's why it is not having any value, so that giving 0. So this one, from the origin, the value of indices along x-axis is 1, so the point will be here. So this is the points along x-axis, and there is no orientation along y and z-axis, so the plane 1, 0, 0 will be this one. And let us consider one more, that is 1, 0, 1 plane. Okay, and for this we shall draw the plane. So we have given for 1, 0, 0, and now we are going with 1, 0, 1. So taking the axis x, y, and z axis. So the indices clearly indicating that the plane is having complete orientation along x, and there is no orientation along y-axis, and there is no orientation, there is a orientation along z-axis, right? So x-axis is the origin, so x-axis orientation is this one. This is the point, and there is no orientation along y-axis, so it will be parallel to the origin, so 0. And there is orientation along z-axis, the full point is this one, right? And now what should do? So we have orientation along x and z axis. So these are the points. Join these 2 points and just draw the line like this. Just draw the line like this in exactly opposite face over here. This one, and this is the 1, 0, 1 plane. This is the plane. So hope you understood. So we have orientation along x and z axis. So we took the complete value 1 and complete value 1, and we joined these 2 lines, and we draw the line in the opposite face, and we draw, this is the plane which is given, that is 1, 0, 1. And now we shall go with a few more examples how to draw the planes by knowing the Miller indices. See what we shall consider. Fine. So -1, 0, and 1. -1, 0, and 1. So this is the plane. So -1 means this is 1 bar, 0, 1. So we have the plane, we have the Miller indices 1 bar, 0, and 1. So if you have the all positive values, if you have all positive values like this, if you have all positive values, it is very much easier to draw the axis like x, y, and z. But here we have the negative sign. So how to take the axis then? It's very much easier. Simple logic, simple technique we have to follow. So shall go in this way. So first shall draw the cubic crystal. Fine. And here we have the -1. So origin cannot be over here. So then we have to create a new origin. So we need -1, right? So shall take axis over here. This is the new origin. So this is the positive, this is negative. This is positive, and here this is negative, and this is positive, down will be the negative. Okay, so this is the origin. This way it is positive, and this way it is negative. So how much it is there? -1. So the point will be here. And there is no orientation along y-axis. So x, y and z. So there is orientation along the x-axis, that is -1, and there is no orientation along y-axis, and there is an orientation along z-axis, that is 1. So this is the positive axis and this is the point. So similarly we need to join these 2 points, and we have to draw one more line parallel to this line in the opposite phase. So joining these 2 lines, and the plane will be this one. So this is the plane having the coordinates in Miller indices -1, that is 1 bar, 0 and 1. So shall go with the last one, the Miller, and how to draw the plane from Miller indices. And the Miller indices will be 1, 1, 1. So this is our plane. So now we shall consider how to draw the plane for this 1, 1, 1. So here we got the cubic crystal, and hope you can observe all our positive values. So x, y and z axis, right? So complete orientation along x axis. So this is the point. So complete orientation along y axis and complete orientation along z axis. This is the point. So we have orientation along all the 3 axes. So join all the 3 points. This, this and this. And this is 1, 1, 1 plane with this origin. Okay. So in this way, by knowing the Miller indices, it is very much possible to find out or to draw the planes, and by knowing the planes, it is possible to determine the value of Weiss indices, and by knowing the value of Weiss indices, it is possible to calculate the Miller indices. Thank you.